These are notes on ideal gases, chapter 14, section 3. So first, just a review of the gas laws you've already learned. So we know that pressure and volume are inversely proportional, so PV equals K, a constant. We know that pressure and temperature are directly proportional. As you raise the temperature, you raise the pressure. So P over T equals K. Similarly, we know that volume and temperature are inversely proportional. V over T equals K. And then we can combine those into what we call the combined gas laws of PV over T equals K. And so that's why all of these initials equal their finals. So P1 V1 equals P2 V2 and so forth. And as we talked about in class yesterday, all of these equations assume that the amount of gas doesn't vary. So we can't calculate the moles of gas in these conditions either. So now we're going to look at an equation where we are going to take the moles of gas into account. So first, let's consider moles of gas. So here we have two identical volumes. Let's assume some things. So we know that the volumes are the same. Obviously, in this one here, we have more moles of gas in this first container than in this one here. So we can assume if the volumes are the same, and let's say the temperatures are the same, that these moles of gas are moving at the same average speed, because we'll assume it's the same gas. And so this one would have a higher pressure, because if the gas particles are moving the same speed and it's the same volume, then we would assume there's more collisions with the side in this one, so this would be a higher pressure. So we can say that the number of moles, we're going to call that N, and the pressure, assuming temperature and volume are the same, we're going to say as number of moles increases, the pressure also increases. Okay, so now let's look at number of moles increasing, and let's look at the volume if temperature and pressure stay the same. So this obviously is going to be higher pressure, and so in order to have the same pressure between the two, we would need a larger volume. So number of moles and volume are also going to be directly proportional. And so you might now be able to figure out number of moles and temperature. So see if you can figure that out by yourself. You can pause it. Assuming pressure and volume stay the same. So if pressure and volume stay the same, obviously in order for these two to have the same pressure with the same volume, this one has to have its particles moving more slowly. How are you going to get its particles to move more slowly? You're going to decrease the temperature. So here's a relationship of number of moles to pressure, volume, and temperature, assuming the other two are constant. So see if you can figure out where the N would go in the combined gas law equation. And then I'm going to show you the ideal gas law. So the ideal gas law is PV equals nRT, or we often in science just say PIV nert, and that's what we call it. Pressure times volume equals moles times R, we'll get to R in a second, times T, which is temperature. So we know pressure and volume are inversely proportional, and we know that temperature and number of moles are inversely proportional. And so that's how we set up this equation. So N equals the number of moles of gas given pressure, volume, and temperature. R then is what's called the ideal gas constant. And that is a constant number that, in a sense, makes this equation work. We could talk about why you need that number, and that's fine if you want to ask in class, but for the scope of these notes, let's just say that is a constant that makes this work. Those of you who took physical science or physics know that, for example, if you have the equation for kinetic energy, you have 1/2 mv squared. The 1/2 is a constant. So the value of R is 0.0821 atmospheres times liters over moles times kelvins. And notice these are the 4 units that are pressure, volume, over number of moles, Kelvin. If you took out the number of moles, this would be the combined gas law. Now we're adding in moles. So these units obviously come from pressure in atmospheres, volume in liters, moles in moles, and temperature in Kelvin. So one of the things to note is if you're using this constant, and you can find other constants in other units, but if you're using this one, you have to make sure you have these 4 units. So let's have some practice here. And I've worked this one out for you. So solve for the moles of gas at 298 Kelvin, 1 atmosphere, and 3 liters. So we have PV equals nRT. Here are the numbers, and I don't have units in here, mostly because I had a student do this and she forgot units. We rearrange it to this and get number of moles. And notice if we cancel our units, the kelvins cancel here, then the atmospheres cancel there because this fraction would be flipped as you multiply. Think about dividing fractions, you multiply the reciprocal. These liters cancel, and we're left with moles, which would be in the numerator because this fraction would flip, so we get 0.12 moles of gas. Okay, so let's look at another practice problem. What is the volume of 0.477 moles of gas at 2.5 atmospheres and 152 degrees Celsius? So now go through and figure this one out for yourself. All right, so the first thing you should see is that we've got degrees Celsius here, and we need degrees Kelvin. So you do 152 degrees Celsius plus 273.15. Accounting for significant figures, we get 425 Kelvin. One thing to note, if you haven't picked this up yet, there's no degrees sign with Kelvin. We just say Kelvin because it's an absolute temperature scale. So now we simply use our Pivner equation, putting everything in except for V, volume. So we get this. Then we rearrange the equation, so we're going to divide both sides by 0.25 atmospheres. So now here we've got our moles canceling here, our kelvins canceling here. This atmosphere would be atmospheres over 1, so when we flip that and do the reciprocal, this atmosphere is going to cancel that atmosphere. We're left with liters, which is what we want. And so we get volume equals 6.7 liters of gas. Now I know some of you are getting lazy, and so you're going to ignore the units the same way our wonderful peer tutor who made this PowerPoint ignored these units. But notice that if you maintain the units, it's a way to check your work. Does this actually cancel and give you the units you want? So if you're confused at how like this atmosphere canceled that atmosphere, please make sure you ask in class so that I can break that down and show you. If you have any questions, please ask them in class or post them on the YouTube comments. Good luck.